Log on, tune in, find out. Another good idea from Cambridge.
And finish heavier, just like in drinking. So the light part will be to finish this kind of nice combinatorics, which, as I said, doesn't work always, but it works to some extent, and we should work out as far as it does work. So let me, for now, for this light part, let me denote by h infinity d the Havana-Flauder-Hecke algebra, affine Havana-Flauder-Hecke algebra. And if I want to emphasize that it corresponds to the quiver gamma, then I'll put gamma in. So corresponding to an arbitrary simply laced quiver gamma over an arbitrary field F. And so if you wonder what that is, I have actually essentially defined it because I defined this for type A infinity, but you saw how type comes in. It just comes into this local situation whether IR is connected to IR plus 1 or not in the quiver, in which direction. So this way, this you can do for any. So I essentially did it for you. And I want to remind you that this infinity in place of lambda means that I just drop the last relation, the cyclotomic relation. So this is defined exactly by exactly as h d lambda of type A, roughly speaking, this cyclic type A or this infinite type A, but for any simply laced quiver gamma, for any gamma, and ignoring the last cyclotomic relation. And I alluded to the fact that actually this seems to be just the right generality to do this combinatorics. It's very easy to say which cyclotomic algebras it will actually factor through, so you don't even want to worry about that. This is a very easy piece of information. And another part which Anton pointed out last time, there are some issues with he pointed out in connection with my claim about reductions modulo P and defining everything over Z, and he scared me. But then we thought overnight with John about it and over email, and it's okay actually, and it is okay because all representations over any field for this algebra are absolutely reducible. It's a theorem of Havana von Laude, and so that basically removes all the technicalities which might require working with bigger rings. So you can indeed work over Z. And so it's a pleasant part here is that I can actually work over any field. And it's not going to matter. You see, even characteristic is basically not going to matter for what I'm going to do. So now we are going to define, or we say, so let M be an HD infinity irreducible HD infinity module. A standard argument again made by Havana von Laude is it's always finite dimensional, and let's assume that it's gradable, or let's assume that it's graded. They're all gradable, and reduce. I should take back what I said about that they're all gradable, because this is an infinite dimensional situation. So I take a reducible graded HD infinity module, and we say that M is pure or homogeneous or calibrated or completely splittable, or Gelfand-Zetlin, or semi-normal, or tame, or skew, etc. If I'm afraid all of these names are used. If you want to, if you ever want to think about these modules, you'll have to invent your own adjective. This seems to be totally in spirit of genre. This is what everybody does. I don't know why it happens here, but this, if you see any of these words, and especially tame is bad here, by the way, but because it means something else. But if you see any of these words, that people probably allude to this situation. And so I might say, if it is concentrated in 1 degree, or which is not totally obvious but easy to see, which is equivalent to the fact that all YRs act as 0. On this module. So you can already see that again this easy combinatorial situation which can be handled can be recognized if you pay attention to gradings. This is kind of a new equivalent reformulation or new equivalent characterization of these modules. That's why I wanted to use the word pure, because this word corresponds to this characterization. Concentrated in 1 degree is sometimes called pure or homogeneous. But there are all these others which correspond to some other look at these things, and they are sometimes not obviously equivalent, and therefore people give different names. But anyway, so this is all the same class, and so it would be nice to understand, and it can be understood very nicely in terms of this rather easy combinatorics, which I began to explain last time. And this is what I want to explain today a little bit more properly. So I want to remind you that we are going to consider bead configurations on abaci, and abacus of type gamma is, we just look at the Dinkin diagram, for type A infinity, for example, again, it will look like this. And then we consider runners which go up. You can do it for D4 or for any other type. And on these runners, we are going to place beads, and the shape of the bead is important. The shape of the bead is obtained by drawing an equilateral right triangle with hypotenuse of fixed size on the bead, and of the size so that it just touches the neighbor. And this size is all of these distances are 1, always. So then this is square root of 2, I think, something like that. So all these triangles are the same. And so in this case, because for this vertex there are 2 neighboring vertices, the shape of the bead will look like this. But in general, there could be more triangles or fewer triangles. Okay, so these are the beads, and then bead configuration is obtained when you just place these beads on the runners of the abacus in order and let them slide as far as they will go, as far as gravity will take them. Then this bead configuration is called the skew shape. If whenever you have one bead, not necessarily of this shape, beads can have different shapes, but on a fixed runner it has a given shape. So if whenever I have 2 beads on the same runner on top of each other, then in between somewhere there should be at least 2 beads on neighboring runners, maybe on the same, maybe on different runners. So this situation somehow implies that there are at least 2 beads in between on neighboring runners. And you can do exercise in type A, infinity, and that will give you the usual skew shape notion, but rotated 90 degrees the way I'm drawing it, so that you get skew shape in Russian notation. And I should also define shape. So this definition is general for any type. I am just illustrating kind of type A. And so you can define shape. It's another silly combinatorial condition. Shape means that whenever you have the last bit on a runner, so there will be no bits underneath. Okay, which is possible. Gravity would take it down, but maybe there are other bits which hold it. So if you have the last bit on the runner, then what should I say? There is at most one bit below it on neighboring runners. There is at most one bit below it on neighboring runners. Okay. Then standard tableau. Well, standard tableau is very easy. Standard tableau is when you play this game of straws, you know, when you try to pull things out without touching anything else. So standard tableau is just when you disassemble your picture, lifting one bit at a time. So you should only you are only allowed to lift a bit which can be lifted without touching the others. So I lift this one. I give it number d. There are d bits on total, so I give it number d. Then I lift the next one, d minus 1, d minus 2, dot, 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 until I disassembled it, and last bit has number 1. So you can think about this as this process, where you remember who went first, who went last. Or I can just place numbers into the bits. So, you know, place numbers, d and so on 1, according to our. In fact, it doesn't matter standard or anti-standard. It would be maybe more convenient to label the bit which you remove first with number 1, and so on the bit which you remove last with number d. So according to the order of removal in our game, or maybe in order of construction, you know, removal or construction. Okay, so is this okay? So you should be able to quickly see that this corresponds to the usual notion of tableau. And what I forgot to say is that shape corresponds to the usual notion of shape, not quite, but almost. In type A infinity, what might happen with that definition is that you might have disjoint union of shapes. You will have a partition, and then another partition which is very far from it, which normally we don't call shapes, but now they will still be shapes because they sort of don't see each other. So they're sort of disjoint, very disjoint unions of shapes. So this is what this leads to. Okay, so now I'm going. So this is some combinatorics, but I'd like to look at this combinatorics. One more piece of combinatorics. I'm sorry. So whenever I have a tableau T, again as usual, I have already alluded to it. I'm going to associate to it. It's what I'm going to call residue sequence. It's going to be an element of I to the d, where d is the number of bits. And as usual, this is I1 ID, where you see these runners, they are labeled by vertices, and vertices, the set of vertices is called I. Okay, so these guys are just going to be labels of the vertices of the Dynkin diagram. And so where IR, it's easy to guess, is the runner label of the bit occupied with R, or labeled R, in our tableau T. Tableau T is labeling of the bits. I look at the bit which is labeled R, it's on the runner. I call this runner IR. In this way, I read off this weight or sequence of labels in the Dynkin diagram. Okay, so now I want to sort of a little bit theorize this picture. If there is what to categorify, then there should be a verb to theorize. Not much, but a little bit. So I want to think about it from a slightly different point of view, and I want to at least bring Coxeter group in for starters. And so I'm going to bring the Coxeter group in the following way. So whenever I have tableau T of shape mu, so let's fix mu. It's going to be, in principle, I can do this for any shape, but I'm going to do it for skew shape only. let's take mu to be a skew shape, and let's take T to be standard mu tableau, or standard tableau of shape mu. So whenever I have such tableau T,
a skew shape doesn't have to be a shape. When you say skew shape,
skew shape it's more general than shape, which is supposed to be an exercise. And tell me if you can see a counterexample right away, but I hope you can't. I'm sorry. Yeah, I'm sorry, I forgot. I mean, there are two axioms for shape. It's a skew shape plus this additional condition.
Oh, okay.
Yeah, you're right. You're spot on. I'm sorry. Shape is a skew shape plus this extra condition. Okay, so now let's go back. I have a fixed skew shape, not necessarily shape. I have a standard tableau. And to this tableau, we associated this residue sequence, IT. And now what I'm going to do is I'm going to send it. You see, all of these i's, they are vertices of this Duncan diagram. So there are simple reflections in the corresponding Coxeter group, which correspond to it. They are called SI's. And so I'm going to associate an element, SI1, SID, in the Coxeter group, corresponding of type gamma. And this element, I want to call it W mu. And you should object right away, but you won't have time, because the first thing I'm going to say is that under the assumptions I made, under the skew shape assumption, W mu depends only on mu, not on the tableau. And in fact, in this way, you get, I believe it's a result of John Stembridge, you get a one-to-one correspondence between skew shapes and what's called fully commutative elements in Coxeter groups. These are such elements where you can go from any reduced decomposition to any other reduced decomposition by doing the only easiest possible Coxeter relation, where you swap two commuting guys, two commuting generators. So some familiar combinatorics comes in. And then moreover, of course, W mu depends only on mu, not on the tableau, but the reduced decomposition depends on the tableau. And in this way, we get a one-to-one correspondence between the standard tableau and all reduced decompositions of this fully commutative element, which I feel is a very pleasant way to think about tableau, and it's completely general. So moreover, part 2 is that we have actually defined a one-to-one correspondence between standard mu tableau and all reduced decompositions of W mu. If I didn't forget some condition somewhere, which I hope by now Arun would stop me. Okay, and there is another very pleasant thing in this game, which you learn rather quickly as you begin to read these papers of people like Stembridge and Proctor and others who wrote a lot about it. That the guys actually have Hooke formula for any type, which I found rather stunning actually. So you can count the number of these reduced decompositions. In other words, you can count the number of standard tableau, provided your skew shape is a shape, which corresponds to another very nice condition on the element of the Coxeter group, which I now forgot. Something like minuscule fully commutative or something like that. So moreover, the last fact which comes from combinatorics is that if mu is a straight shape, or shape, I just said shape. If mu is a shape, then the number of standard mu tableau, they don't speak in these terms, of course, they speak in terms of this amount of reduced decompositions, but because of that, the amount of standard mu tableau is given by the following remarkable formula. It's d factorial, of course. And now you're supposed to see the product of the hooks. Well, so what is going to come instead of the product of the hooks? Well, It's going to be the product over all roots alpha in phi of W mu height of the root. Okay, where phi of W is the number, it's a well-known set, it's a number of positive roots which are sent to negative roots by W inverse. So this, the size of this set is precisely the length of W. And an exercise is to see, very easy exercise, is just to do the definition chasing and see that in type A infinity, this is precisely Hooke formula, nothing else. Which for me always was kind of the most mysterious ingredient of this elementary story, and I always thought it was both kind of intimidating and beautiful thing. But it would be nice to really understand why it is obvious, and I don't think we yet quite understand why it is obvious, but we are getting closer, because I mean when you're getting something like this, it's already quite theoretic, and so there is a chance to actually make it obvious eventually. So anyway, this is pure combinatorics. So really, I only care about Hooke formula. Say it again. I didn't say it's obvious, but I said with this formulation, there is a chance to one day see why it is obvious. Yeah, I'm not. It's still not obvious. No. But you see, before there was no chance. I mean, you can read all those beautiful.
That's why there's still no chance.
Okay. that may be, you know, a pessimist, optimist, but agree that this is nicer than what we had before. No? Come on, it's a general type. It's not just some gimmick in type A or something like that. Anyway, so it doesn't matter. The next remark which I was going to make was that for me the Hooke formula is only good when it computes dimensions of some irreducible modules. Otherwise, I don't care. Right? So it computes something, which is very nice, but really, in representation theory, we like Hooke formula because it computes dimensions of irreducible representations. So this is what these Havana-Lauda Hecke algebras provide. They provide us with actual representations for whom this formula computes their dimensions. Okay? And so the theorem is very easy. It's just as before. It's just like for symmetric groups. So let mu be a skew shape. T of mu be the set of standard mu tableau. Define module. So set S of mu, Specht module, simple module if you want, to be for starters as a vector space with the basis labeled by standard tableau. The formulas first I act with an idempotent E of j Vt, and it's delta Itj or delta j It Vt. So idempotent projects to the weights, and the weights are precisely these It sequences. Yr acts as 0 because we only care about such guys from the beginning. And finally, psi r is as nice as you could possibly dream. It's just trying to be a transposition, if it can, and then 0 if it cannot. So psi r Vt is V SRT if SRT is standard, Same formulation as for symmetric group. And 0 otherwise. So these formulas define an action or define a representation of h d infinity on S of mu you can see that by definition this representation is pure, or by our second definition, it's irreducible, and all such where mu runs over skew shapes with d bits is a completely redundant set of pure representations. Set of irreducible pure modules over this algebra. Moreover, well, I didn't say you the degree, but degree is going to be boring. It's all going to be in 1 degree. You can take any degree, concentrate in it. Moreover, just like for symmetric groups, if mu is a straight shape, then the dimension of S mu is given by the Peterson-Proctor Hooke formula. I forgot to say this Hooke formula is usually ascribed to Peterson and Proctor. Peterson unpublished. And Proctor, as far as I'm concerned, is also unpublished. But maybe it's somewhere. Yeah, but it's published now, but not by these two people. So finally, then the dimension of S of mu is given by that Hooke formula, which I written down. So by the Peterson-Proctor Hooke formula. Okay, so this is the end of this easy story. This nice story. Okay, so now we want to go sort of general case and see what we can do. Now there are more modules, more irreducible representations. So if there are no questions here, just go there. Okay, so now let's return to type A, or let's return to our setup from the previous 2 lectures. So return to the setup where h d lambda is cyclotomic Hecke algebra. With parameter psi over the ground field F. So we are back in this both more and less general situation. So now we have only special type because we only have the cyclotomic Hecke algebras, but we are not assuming that modules are pure. We are going to consider all modules. Well, remember that these cyclotomic Hecke algebras are easy to decompose into blocks. So really, this HD lambda can be written down as a direct sum of the blocks H alpha lambda, where alpha is running through all Q pluses such that the height of alpha, which does not have to be a root, just any non-negative linear combination of simple roots, and the height, which is the sum of those coefficients, is equal to D. And the remark also was that some of this might be 0. But those which are not 0 are blocks. And then as Joe explained to us, and in larger generality, but it's exactly the same part of the story and exactly the same notation, that for any I in I and any n greater than or equal to 0 non-negative integer, there exist functors ei to the n and fi to the n, and they can even be defined on blocks, and it's actually the most convenient thing to do them on the blocks. So the function ei to the n goes from the graded modules over the block h lambda I to the graded modules over the block h lambda I plus n alpha I. It's trying to add this root ei, this function ei to the n is trying to add n copies of the simple root alpha I to the block label. And then there is an adjoint function fi to the n. Actually, I have to be a little bit careful. If you want it to be adjoint in the graded category, you will have to shift a degree. So let me take adjoint back. In the ungraded category, it will be adjoint. But it's easy to say how to shift to make it adjoint. But let's not worry. So this one is trying to subtract n copies, n lots of alpha I. Okay. And then there is a third functor, which is not usually introduced because you see these guys sort of correspond to Chevalier generators, and then Chevalier generators generate. So you don't need ki's in the quantum group or hi's. But it's so easy to say what ki's are, so that I might as well. The third functor is going to be ki, and it's just going to be the shift, the degree shift by a specific value. So the functor ki on the graded category is going to send m, which is a module in h lambda alpha mod, and it's going to send it to the same module with degree shifted by a prescribed value, which is lambda minus alpha alpha I. So again, this is this Lie theoretic notation. Lambda is the dominant weight. I subtract alpha, and I take brackets with alpha I. So this is an integer. So you shift by that. Okay. So now let us consider the Grothendieck group, the big Grothendieck group for all of these blocks. Give it some name. Or maybe I'll just denote it in brackets. So, okay. So I guess even before taking Grothendieck group, I can just take direct sum of all those algebras. So let me denote by h lambda g mod direct sum of the categories over all alpha or all blocks or for all of these guys. So it's going to be sum over all alpha and q plus. This is what all the blocks of all ranks are labeled by. So it's the same as I would take sum of HDs over d greater than or equal to 0. Okay, so I take the sum over all these guys of h lambda alpha g mod. And let's consider the Grothendieck group of this thing, which I'll just do brackets for. So this is the Grothendieck group. And this is a free infinite rank ZQ inverse module. Usually Grothendieck group is just a Z module, but because we deal with a graded situation, we can shift degrees up and down. We can associate shift up by 1 to multiplication by q, and that gives us this structure. Okay, and then these functors were exact, so they will produce linear operators, which strictly speaking I need to denote the same functors in brackets, but I will forget brackets, so I'll use the same names. So now ei to the n, fi to the n, and ki become operators, linear operators. On this Grothendieck group h lambda g mod. Okay, and so the idea is very well known by now. Idea is to sort of identify what do they generate, what kind of module we get, and all of that can be done And then the idea is to push it as far as possible and, to get to reap some harvest, maybe in both directions. So here's the theorem, which I think I will probably it will probably have many parts, but I'll sort of state them and I comment as I go. Okay. And I will also try to ascribe the authorship and things like that, also as I go. Okay, so first part is that the elements ki, ei to the n, and fi to the n. For that you only need ki, ei, and fi, but since divided powers is easy to define almost as eis and fis, so why not? So they satisfy the defining relations of the quantized enveloping algebra corresponding to the Kac-Moody algebra G, which I introduced last time, of the corresponding type A infinity or the cyclic quiver. And therefore, which makes our Grothendieck group H lambda G mod into a module over this quantum Kac-Moody algebra. And the question is, what module do you get? And the statement is that you get the module is highest weight lambda, where lambda is the same lambda as the one which labels the cycloatomic quotient. And at least now you can see that this notation was justified. It makes a lot of sense to actually do it, because Lie theory is not artificial here, is not just some silly placeholders, but it really is relevant to what's going on.
So lambda is reducible?
Yes, it's an irreducible module with highest weight lambda. Infinite dimensional, but.
Can you say something about why the cycloatomic condition forces Fi to the right power to vanish?
Well, because cycloatomic condition is a condition on, it's not so obvious, but it's roughly speaking it's a condition on how large of a Jordan block you might have, but on x1. Okay, so it's actually not so easy to translate to the last position, but that's essentially what Ian Granovsky does, for example, in his paper. So maybe some authorship needs to be mentioned here. In the ungraded case where you also don't have a quantum group, so you just have U of G. So this theorem was it's really hard in the subject. At least for lambda 0, it was first observed by Lascoli, Clerc, and Thibon. And then for the cycloatomic case, it was done by Ricci and Granovsky. So all of that is at q equals 1. And that the graded situation provides a quantization as it should. We observe with John Brandon. We didn't post a preprint yet, so I guess it should be marked as 09. So this is for any q. So this is at q. Okay, so now under this identification, many nice things identify, and you can sort of spend a long time explaining what gets identified how. But let me move a little bit in that direction and show you whatever time permits. So maybe I'll make a little table, but I think I'll probably make it there in order to have more space. So let me have sort of this Kac-Moody world, or this module on the left, and our representation theory, our Grothendieck group on the right. So you might say, what is the highest weight vector? And this is really silly. So under this, the highest weight vector corresponds to the module in the Grothendieck group, and this corresponds to this kind of smallest degenerate case when alpha is equal to 0, And when alpha is equal to 0, then you'll have to interpret your algebra as f, just a copy of the field, and the module is f. So this is sort of the silliest module f, or its class in the Grothendieck group, for the trivial module over the algebra H0 lambda, which is isomorphic to f. Carefully look at the definitions. This is how it should be interpreted. Okay. So this is very easy. Then it's also not so hard to see because of the way we define the action of KIs. You see, KI essentially shifts by the value which corresponds to the weight space, or rather to the action of alpha I on the weight space. So all I'm trying to say is that the weight space lambda minus alpha under this identification just corresponds to the natural direct summand of this big Grothendieck group, which is a small Grothendieck group, corresponding to the modules over the block. Okay, now this place resembles me that I forgot to say something. Strictly speaking, I define the Grothendieck group as ZQQ inverse module. And the quantum group and the module is defined over the field, not over the ring. So I need to, not to complexify, but to extend scalars to C of Q. So I guess here are two. I need to do something like that. Okay, because really, this module is over this field. Okay. But there are no reasons to forget about lattices, because you see this is a lattice in this, and these lattices can actually be identified, and they get identified in a very nice way. So in every highest weight module there are usually two lattices at least, which are important. One lattice is sort of this minimal lattice when you take the highest weight vector V lambda and you hit it with constant Tietz Lustig Z form. And then you get some sort of Z form, ZQQ inverse form. Then you get a lattice. And you might think that the lattice which you get here is just going to be that lattice, which is false. And then there is a dual lattice, which can say there is a Shapovalov form, and then you consider all elements which pair integrally with the original lattice, and integrally means that, with respect to the Shapovalov form. So there are these two lattices, standard lattice and costandard lattice, which are dual with respect to the form. Okay, and so it turns out that this is the costandard lattice, so I'll write it down. So if you don't extend scalars, just consider lattice. Then it corresponds to the dual. What should I say? So let's say this is the Lustig Z form of the module, and so it's the dual one. And then this corresponds just to H lambda mod without extending scalars. And then what should this correspond to if you don't dualize? And this corresponds to the this was all modules, and then it corresponds to the lattice which comes if you consider the Grothendieck group of projective modules. I'll say G proch. Okay, so in general, this does not embed into that, but it's proof that for the cyclotomic Hecke algebras it does. And so this is a smaller lattice, and then this is a dual bigger lattice, and so you get that. So this.
I'm sorry, can you explain the third one again? I thought that H check G mod was the whole category we were considering.
It is the whole category. This is a category of all finite dimensional graded modules.
But didn't that categorify?
Inside of that category, there is a smaller category of all projective modules. And so they give us two lattices over our ground chain ZQQ inverse. And in this situation, this is embedded into this. This Grothendieck group is embedded into that Grothendieck group, and they can be identified as two very natural lattices in this module. And in fact, the Shapovalov form itself can be identified very nicely as just taking the dimension of the whole space in this category. So the home is the Shapovalov form. So I'll write it down next. But before I do that, I should say that again, this result, I believe, is due first to Grainovsky in the q equals 1 case, and at arbitrary q we do it with Brandon.
The first mod, should that be G mod or not?
Excuse me?
H alpha lambda mod, is that G mod?
Yes, every mod is G mod.
Okay.
All modules are graded modules.
Yeah.
So it's G mod, G proch, and so on. Okay, so then I promised the Shapovalov form. So Shapovalov form on V of lambda gets identified with the Cartan form, is what's sometimes called, on H lambda approach. You see, it's enough to define Shapovalov form on the lattice, because when I extend scalars, I get the whole thing. So I might as well define it on this lattice. And on this lattice, it's something very natural representation theoretically. By this I mean that I take class of projective module P, and I want to pair it with a class of projective module Q, and I will just define it to be the Q dimension of the graded vector space home over H lambda from P to Q. So they are graded, so this is a graded space, so Q dimension as defined last time. So you get Laurent polynomial, and then this is how Shapovalov form gets identified. And I believe again at Q equals 1 this was done by Grainovsky, and at any Q we do it with Brandon. Now something which does not make sense at Q equals 1 is the bar involution. And the claim is that the bar involution on the left just corresponds to duality on the right. So you have, whenever you have a module over cyclotomic Hecke algebra, there is a natural notion of dual, because cyclotomic Hecke algebra in the Khovanov-Lauder-Ruquet presentation has a natural homogeneous anti-automorphism, which is identity on the generators. And so you can use this anti-automorphism to define the duals. And the claim is that the bar involution is precisely what you identify it with if you push it to the Grothendieck group. Okay, so number 6. So this could not be done before, because it's only been done at Q equals 1. So this I should say. So it'll work, although it's not very hard at all. And then next one is there is a standard spanning set. I'd like to say standard basis, but I should say spanning set, because these elements are actually going to be linearly dependent. And let me finish the sentence, and then I will tell you what I mean by that. It's labeled by certain mysterious lambdas. Corresponds to the classes of Specht modules appropriately graded, so that we can consider them as a class here in the Grothendieck group. So this is appropriately graded Specht module. And again, by general nonsense, there is essentially unique such grading up to a shift. Up to a shift in automorphism, but automorphisms are trivial for the Specht module. So we construct those gradings explicitly, and then this module becomes an element of our Grothendieck group. And so now I just have to tell you what I mean by the standard basis. And so in order to do that, you need to consider the corresponding Fock space. So V of lambda can be obtained either as a submodule or quotient module of the corresponding Fock space f of lambda, which is not irreducible. but which is a nicer module because it has a natural basis. And this natural basis, m lambda, now it is indeed a basis. And this basis is labeled by all L multipartitions lambda. So when you consider level 1 Fock space, it's just all partitions. And when you consider higher level Fock space, by which I mean appropriate tensor product of the level 1 Fock spaces, then it has a basis which is labeled by multipartitions. And there are formulas for how to act here, and this is a relatively well understood module, but it's clear that the highest weight here is capital lambda, and therefore there is such a homomorphism phi, and under this homomorphism we can send these m lambdas to pi of m lambdas. Now they are not going to be a basis, they are just going to be natural spanning set. Now they could be linearly dependent, and this is what I call S lambdas, standard spanning set. So even though they are not a basis, they are still very nice. And actually, from the point of view of categorification, you should understand we shouldn't expect them to be a basis because Specht modules are not linearly independent in the Grothendieck group. But we can still identify these guys, and this is actually very important if you want, if you actually want results along the lines of LLT conjecture, because you really want to compute canonical basis. But what does it mean to compute canonical basis in terms of some other well-understood basis? Only then it will be useful. And if you can identify this other well-understood basis or spanning set with something which you understand on the representation theory side, then you're just trying to write down simple modules in terms of Specht modules. And if you didn't do that, then it's not as useful for representation theory. So this is actually worth doing. Okay, so and again, this part has been done by Hecke at q equals 1. And by Brandon and myself at arbitrary q. One thing which I should mention is that grading Specht modules is our joint work with Brandon and Wei-Chan Wang. Okay. And okay, so then you can also identify, I will not be too detailed here, but you can also identify the crystal graph with the Sokol branching rule. And it's been done in two different ways by Hecke and Grajnowski. But then here again there are some new issues which you might ask. For example, you know, when there is a branching rule, if you know these results, then you know, okay, you look at the Sokol, what appears in the Sokol, but then there is also a very nice result about what is the multiplicity of this guy who appears in the Sokol. And it's precisely this parameter epsilon I from the crystal graph which was mentioned by Joe. This is this parameter which they use to stratify. So this is this well-known epsilon I of B number in crystal graph, epsilon I and phi I. And so these numbers, they correspond to the multiplicities in the branching rule. And then you can say, okay, so now we can speak of the graded multiplicities. So there is still some work to be done. What are the graded multiplicities? Because we are now doing grading representation theory. And the answer turns out to be as nice as you can hope for. All you have to do is, you have to do this. So the graded multiplicities will be the corresponding quantum integers. So there is still more work to be done here in the branching rules, and some of this we also do with Brandon. So we sort of contribute more to this graded branching, which fits very nicely some of the Kashivara results on the dual canonical basis. Because there is this result about what happens if you do EI to the dual canonical basis element, and there is this leading term, and this is precisely what the multiplicity should be. If you do EI, and this is what you do FI. So in that sense, there is a complete match. Okay, so now I have 5 minutes left. Let me tell you a little bit more. So these results are quite nice. Can we make it a little bit more concrete? So one thing which you might want to have is classification of simple modules. You know, you might want to label simple modules by some p-regular partition, so as it is usually being done. And I should mention it can sort of be done here, because all you have to do is this crystal is completely explicit in the sense that you can define a crystal of the Fock space, and it's going to be crystal on all multi-partitions. And there are some explicit rules which tell you when there is an error, and it's something like you have to add certain I box, or you cannot add an I box, or you can remove an I box if it's good, as sometimes it's called, and all these standard rules. So this is a completely explicit thing. And then, but this, of course, this is not an irreducible module. So you would like to see the crystal graph of this irreducible component, and in order to do this, you just take the empty multi-partition and look at its connected component in the crystal graph. And that will give you the labeling set for the irreducible modules here. And in fact, it can be proved, and it was done by Hecke, that this labeling set, which you will get if you define this crystal graph properly, there are some choices to be made, corresponds precisely to the irreducible modules obtained from Specht modules using the usual cellular theory. Okay, so and this is something which I want to write down because I didn't say it very well. So let me write at least something down. So let us let me say the crystal graph of f of lambda is a graph whose vertices are all L multi-partitions where L is the level of lambda, sum of the coefficients. Okay, so you consider all multi-partitions, infinitely many, because you consider multi-partitions of all numbers. And then there are precise rules. So it has these vertices, and arrows are given by some precise rules, but which are a little bit subtle. And then you take the empty multi-partition, L copies of the empty partition, and you generate whatever you will generate. And Meinhof already mentioned that it's not a piece of cake to actually say what you generate. Okay, but we might call it whatever gets generated by these explicit rules. It's an inductive definition. Will be called regular multi-partitions. And they're called this way because if you do it in level 1, you will get the usual p-regular multi-partitions, which means that just like in the usual modular representation theory of symmetry group, repetitions of p or more parts are disallowed. And this is just a generalization of that for multi-partitions, but as Meinhof pointed out, it's not an obvious thing. In fact, it's rather hard to do this, but we don't care. So whatever you get some class of multi-partitions, and then Hecke proves that in the ungraded theory, but it doesn't matter now. It's just a general thing that so Specht modules are the cell modules. This is not what Hecke proves. So this is Dipper, James, and Mattes. So Dipper, James, and Mattes construct a cellular structure on the cyclotomy Hecke algebra. So it comes with cell modules, which is what we call Specht modules. And then there is a general theory. There is this form, remember, and we consider radical of this form. We kill it. Sometimes radical is everything. When is it not everything? Then when it is not everything, it gives you simple module and a quotient. So you can have d lambda as s lambda minus radical when non-zero. And that will give you all irreducible modules. And the theorem of Hecke is that these irreducible modules are precisely labeled by these regular partitions. Okay, so it's not zero precisely when that condition is satisfied. So the thing is that this thing is not zero if and only if lambda is regular multi-partition. Okay, in some sense, the fact that crystal graph vertices of crystal graph corresponds to the simple modules was also proved by Granovsky, but not quite with this degree of precision, so that you can't identify modules which appear in the heads, the Specht modules precisely, via this precise crystal graph. And also these modules are self-dual, which again is a general part of this cellular theory. Okay, so then the main problem, as usual, is to understand it's a classification in some shape, and it's probably as reasonable as one might hope, even though the labeling set is defined inductively. And then one remember I mentioned that ideally we would like to understand the Q characters of irreducible modules. And so the best result available here is Hecke, who proves that if characteristic of the ground field is equal to 0, then the G lambdas in the Grothendieck group at Q equals 1, so if I get gradient here, I don't know how to use the notation if I get gradient, I'll put a bar on top. So you consider ungraded situation, and so this is the dual canonical basis. So all D lambdas form a dual canonical basis in V of lambda, again at Q equals 1. And this is a very nice result because Specht modules have been identified and canonical basis is computable. I mean, it's very definition in some senses, just like journalistic polynomials, but there are better algorithms due to Lasculi-Clark-Timon and others. You can compute canonical basis in terms of S, in terms of this basis S of lambda, or spanning set S of lambda. And because of the Hecke, while you compute this, well, you'll get some polynomials, then you evaluate those polynomials at 1, and you have expressed irreducible modules in terms of the Specht modules, which gives you at least dimensions and characters. So this is at Q equals 1, but we believe that we can prove the same thing without putting Q to 1. So we can just say the same at Q. So you don't have to put Q to 1, you just consider the class and the gradient Grothendieck group. And this will form canonical basis, or dual canonical basis of V of lambda, not at Q, but just over Q. And so you don't have to put those polynomials to 1, they actually compute to your graded multiplicities, and therefore you can also find, this gives you an algorithm for finding the Q characters of simples, because we know the Q characters of Spechts explicitly. So in some sense it's a pleasant situation, but remember, this is only provided characteristic is equal to 0. So it's a result for root of unity over complexes, but it does not give you a characteristic P result. So James conjecture is as evasive as always, as usual. So this really is not a big contribution towards there. And I should say that the way we prove it, of course, we use Hecke theorem. So it's kind of a major part of this. Okay, I think I'm sorry.